All right, welcome to the second stage deep learning in NLP part 3. Let's get started. So previously, we acquired our tools to create representations, 3 representations per input word, right? So basically what happens, as was mentioned earlier, you get an input word, you have some embedding representation of it. From that embedding, you need 3 different representations, as discussed before. And, the tools in our toolbox that make that possible are these matrices, WQ, WK, and WB. Now let's see what happens. So let's take a look at one word. Right? Let me give quick definitions of these Q, K, and V vectors. All right. So your Q vector looks at your word, is kind of in your new self-attention mechanism. It represents the querying function. So basically what happens is that your x1 over here, which is a representation for the word thinking, that has 3 vectors, q, k, and v1 associated with it, will have a q1 querying every other word in the sequence. So this sequence is a very simple one. It has just 2 items, thinking and machines. And your Q1 queries thinking, and then queries machines. What querying here does is, taking a look at the key of each item, and by taking a look at it, basically means dot product. So this will determine how much attention the present word, the querying word, should pay the queried word, the word that holds the key of the word that is being queried, right? Okay, so with Q1 goes around, take a look at key corresponding to the first word, K1, and figures out magnitude of an attention. Does the same thing. So Q1 again does the same thing to the key of the second word, and outputs the magnitude of an attention, right? So I pay this much attention to the second word as the first word, and as the first word I pay 112 much attention to myself, right? Okay, so that's basically what query and key do, right? Beautiful. So if you want to do the same thing with machines, you take a look at the Q2. So use the Q2 to query every other word in the sequence. So the Q2, multiplied by K1, and then Q2 by K2, right? They would get the sort of magnitude of attention for the word machines. But right now we're just looking at word thinking, so we're using Q1. Okay, great. Now what do? First of all, it's scalar. We want it to be, we want it to be a ratio. We want it to be a value between 0 and 1 to be called attention. To achieve that, we have a softmax layer that takes scalar values as input and outputs values between 0 and 1. So with the dimensionality of Q and K growing in size, it's very likely to get, it is likelier to get, higher scalars as output. And this may push our output to the regions with, smaller gradients. To counter that effect, we divide these scalars, or these magnitudes, by the square root of the dimensionality of our Qs or our keys. They're the same. They basically, each one is 64 for the original transport network. If you divide that, you take the square root of that, it's 8. So you divide by 8. All right, and then as mentioned before, pass these values 14 and 12 through a softmax layer, and there you go. You got your attention. So this word is paying a lot of attention to itself, a little bit of attention to the word next door. But we're not done yet. The purpose was to create a tended over representation, right? Not just the attentions, right? Okay, that's why we needed the v values. So we've already used the q vectors, we've used the key vectors, I'm familiar with those. Now we're about to use the v vectors. Okay, so basically, simply you multiply your v vector by your corresponding attention. So for your v1, use the q1k1 attention and weighted by that, so by 0.88. And for v2, you use your q1k2 attention, which is 12%, 0.12. Right? So multiply V2 by this value, and you get your, weighted, V2. Last but not least, you just sum them up, and get your Z1. Remember, this is Z1. It is a representation over the entire sequence, a weighted representation over the entire sequence, but it corresponds, to the word, to the first word, the ith word, to the first word. So x1. So basically, you can throw any number of these words theoretically in parallel at your parallel computing device, and in isolation. They don't have to. So for the same representation for the word machine, which is Z2, doesn't really have to wait for Z1 to be created. Okay, let's do a quick recap. Basically, you get your Q, K, and V vectors by multiplying the initial embeddings by the corresponding matrices. All right. And you get these matrices, corresponding to a number of Qs, a number of Ks, a number of Vs. Okay, good. Then you multiply, as was mentioned before, relevant, Q and Ks, which will, translate into a simple matrix multiplication. You use your normalization term to reduce the output range, as was mentioned earlier, and then you multiply that by the V matrix. I put the dot product equation here for you to observe that this product grows, with the dimensionality of Q and K. So it's likely to grow when the dimensionality of Q and K increases, right? Great. Now you know exactly how a self-attention sublayer works. In the next video, we're going to talk about attention heads.